Find somewhere comfortable. You don't need to sit up straight or hold any particular thought in your mind. You don't need to remember any of what follows or understand it completely or do anything at all with it. Just let the words arrive the way sounds arrive through an open window at night, present, soft, and already fading before they fully landed. Tonight we're going to travel somewhere unusual, not far away exactly, more like very, very deep, down beneath the surface of things, down beneath the chair or the bed you're resting on, beneath the floor, beneath that, beneath the earth, beneath the atoms in the earth, all the way down to a level of reality that most of us never think about. And yet it is the level at which everything, including you, is actually happening. The universe, it turns out, is not made of things. It is made of something older and stranger and quieter than things. It is made of fields, vast, invisible, patient fields that stretch through every corner of space, that pass through walls and through planets and through you as you lie here, that have been present since the first moments after the universe began. And what we call particles, electrons, photons, quarks, the building blocks of every atom in your body, are not tiny objects sitting in those fields. They are the fields moving. They are ripples. They are the ocean briefly disturbed. That image is worth sitting with for a moment before we go any further. The ocean briefly disturbed. We're in no hurry tonight. There is a picture of matter that most of us carry somewhere in the back of our minds, even if we never consciously placed it there. It is the picture of the atom as a tiny solar system, a dense nucleus at the center, and electrons orbiting around it like small, dutiful planets. The nucleus is made of protons and neutrons, which are themselves made of even smaller things called quarks. And at the bottom of this nesting, at the very smallest scale, sit the fundamental particles, the truly elementary ones, the ones that cannot be broken down further. Infinitely small, perfectly solid, discrete little points of matter, each one sitting in empty space, each one a distinct and separate thing. This picture is wrong. Not slightly wrong, not approximately wrong in the way that a map is wrong when it flattens a curved surface. It is wrong at the level of the underlying idea. The fundamental things are not dots sitting in space. They are not objects at all in any sense that we would ordinarily recognize. The universe is not a collection of things. It is a collection of fields, and the things we call particles are what those fields look like when they are disturbed. To understand why physicists were pushed toward this picture, it helps to follow the chain of confusion that led them there, and the confusion begins, as so much of modern physics does, with light. For most of the 19th century, light was understood to be a wave. This was not a guess or an intuition. It was the conclusion of careful, meticulous experiment. When light passed through two narrow slits in a barrier, it produced an interference pattern on the screen behind, a series of alternating bright and dark bands, exactly what you would expect if two sets of waves were overlapping and either reinforcing or cancelling each other. Waves do that. If light were made of tiny bullets, you would expect two clusters of impact marks on the screen, one behind each slit. Instead, you got the striped pattern of interference. Light was a wave. The matter was settled. And then, in 1905, Albert Einstein looked at a different experiment and concluded the opposite. When light shines on a metal surface, it can knock electrons loose from the metal. This is called the photoelectric effect. But the strange thing was how it worked. You might expect that a brighter, more intense light would knock electrons out with more energy, like a stronger push. But that is not what happened. The energy of the ejected electrons depended not on the brightness of the light, but on its color, on its frequency, the rate at which the wave oscillates. Dim violet light knocked out electrons with more energy than bright red light, and below a certain frequency, no electrons came out at all, regardless of how bright the light was. Einstein's explanation was that light did not arrive as a continuous wave, but as discrete packets of energy, what Planck had already called quanta, and what we now call photons. Each photon carried an amount of energy determined by its frequency. A photon of violet light carried more energy than a photon of red light. If a photon's energy was above a certain threshold, it could eject an electron. If it was below, it could not, no matter how many of them arrived. Light was, in some sense, made of particles after all. So which was it? Wave or particle? The answer, deeply and genuinely, is that it is neither. It is something that, depending on how you look at it, resembles one or the other. And this is not a limitation of our instruments or our cleverness. It is a feature of reality itself. The same experiment, performed with a single photon at a time, still produces an interference pattern over many repeated trials, as though each individual photon somehow passes through both slits simultaneously and interferes with itself. And yet, when you try to detect which slit it actually went through, the interference pattern disappears, and you get two clusters, the particle result. The act of looking changes what you find. Electrons behave the same way. They too produce interference patterns when passed through slits. They too seem to pass through both at once when unobserved, and through one when observed. Louis de Broglie proposed in 1924 that every moving particle has an associated wavelength, and Erwin Schrödinger wrote down an equation describing how this wave-like property evolves through space and time. But the wave is not a physical wave in the way that a water wave is physical. It is a wave of probability, a description of where the particle is likely to be found, spread out across space, until the moment of measurement collapses it to a single location. The framework that eventually made sense of all this is quantum field theory, and its central claim is that the question of whether something is a wave or a particle is a category error, like asking whether a musical note is a vibration or a sound. The answer is that there is a field, and the field has both wave-like and particle-like aspects, and neither description is the fundamental one. The field is the fundamental one. Picture, then, the whole of space, not just the space in this room, not just the space of the solar system, but all of space, from here to the furthest reaches of the observable universe, filled with a set of invisible fields, one field for electrons, one for photons, one for each type of quark, one for the particles that carry the weak nuclear force, one for the Higgs. Each field is everywhere. Each one passes through every other. They do not compete for space or push each other aside. They simply coexist, overlapping, present everywhere simultaneously, like different pieces of music playing in the same room. In their quietest state, these fields are not nothing. They are not empty. They are simply undisturbed. They have a ground state, a baseline condition of minimum energy, and in that state they are as still as they are ever permitted to be, which, as we will discover later, is not very still at all. When energy is added to one of these fields, when something disturbs it, the field develops a ripple. That ripple is localized. It moves through the field with a definite speed, a definite momentum, a definite energy. It behaves in every way that an experiment can detect, like a particle. But it is not a particle in the old sense. It is not a little ball. It is a wave packet, a region of the field where the oscillations are concentrated, where the field value is temporarily elevated, moving through the background of the field the way a wave moves through the ocean. The ocean does not travel when a wave passes through it. The water itself moves up and down, but it stays roughly where it was. The wave is a pattern of motion, not a moving piece of water. In the same way, an electron moving through space is not a piece of the electron field traveling from one place to another. It is a pattern of excitation in that field, propagating through a field that is already everywhere. This is a genuinely strange idea. It asks you to let go of the intuition that matter is made of stuff and replace it with the idea that matter is made of behavior, patterns in something more fundamental than matter itself. The fields are more real than the particles. The ripples are what we see. The ocean is what is actually there. And that ocean, it turns out, has a history as long as the universe itself, and a set of people who, over the course of about half a century, worked out its nature with extraordinary patience and ingenuity. The story of how physicists arrived at this picture of the universe is not a story of clean insight and confident progress. It is a story of discomfort, of brilliant people being forced, against their own preferences, to accept ideas that seem to violate common sense. It begins, quietly, in the year 1900, in Berlin, with a man who did not particularly want to start a revolution. Max Planck was a careful, conservative physicist. He was not the kind of scientist who enjoyed overturning established ideas. He had been trained in classical physics and believed deeply in its methods. When he turned his attention to the problem of black-body radiation, the way a heated object glows, he was not trying to discover something new about the nature of reality. He was trying to fix an equation. The problem was this. When you heat an object, a lump of iron, say, or a glowing coal, it emits light across a range of frequencies, and the distribution of that light follows a specific pattern. Physicists had equations that described different parts of the spectrum reasonably well, but no single equation worked across the whole range. In particular, the classical equations predicted that a hot object should radiate infinite energy at very high frequencies, a result so absurd it was called the ultraviolet catastrophe. Clearly something was wrong. Planck found, through careful mathematical manipulation, an equation that matched the observed data perfectly. But to derive it, he had to make an assumption that he himself found deeply uncomfortable. He had to assume that the vibrating atoms in the hot object could only emit or absorb energy in discrete chunks, whole number. They could not emit any arbitrary amount of energy. They could only emit 1 unit, or 2 units, or 3, where the size of the unit depended on the frequency of the vibration. He called this minimum unit a quantum, from the Latin word for how much. Planck believed, at first, that this was a mathematical trick rather than a physical truth, a convenient fiction that happened to give the right answer. He spent years trying to find a way to derive the same result without the quantum assumption, and he failed. It was Einstein's 1905 paper on the photoelectric effect that convinced the broader physics community that the quantization was real, that energy genuinely came in packets, not as a continuous flow. Planck accepted this conclusion with something close to reluctance. He had not meant to change physics. He had meant to save it. The thread he had unwittingly pulled would unravel the entire fabric of classical physics over the next 3 decades. But it was a young British physicist working in Cambridge in the late 1920s who wove something new from the loose strands. Paul Dirac was, by most accounts, one of the most original minds in the history of science. He was also famously quiet. Colleagues joked that the unit of 1 word per hour should be called a Dirac, and his approach to physics was characterized by an almost aesthetic pursuit of mathematical elegance. In 1928, he set himself the task of writing down an equation for the electron that was consistent with both quantum mechanics and Einstein's special theory of relativity. Special relativity, developed by Einstein in 1905, describes how space and time behave when objects move at speeds approaching the speed of light. At those speeds, time slows down, lengths contract, and the relationship between energy and mass becomes deeply intertwined. The quantum equations that existed at the time, Schrödinger's equation in particular, worked beautifully at low speeds but were not consistent with relativity. Dirac needed an equation that satisfied both sets of rules simultaneously. He found one. The Dirac equation is one of the most beautiful results in all of physics. It describes the electron with perfect consistency across all speeds. but it came with an unexpected passenger. When Dirac solved his equation, he found that it did not have one set of solutions, it had two. There were solutions describing the ordinary electron, as expected, and there were solutions describing something else, a particle with the same mass as the electron, but with the opposite electric charge, a particle that had never been observed. Dirac was initially uncertain what to make of this. He considered the possibility that the second set of solutions corresponded to protons, since protons were the only positively charged particles known at the time. But the mathematics was clear. Whatever this other particle was, it had to have exactly the same mass as the electron, which protons do not. Protons are about 1,800 times heavier. In 1931, Dirac made the bold prediction: there exists an anti-electron, a particle identical to the electron in every respect except that its charge is positive. He called it the positron. The following year, Carl Anderson observed exactly this particle in cosmic ray experiments. High-energy particles arriving from space, leaving tracks in a detector that curved in the wrong direction for an electron in a magnetic field. The positron was real, and with it, the concept of antimatter was born. What Dirac had discovered, almost as a byproduct of trying to reconcile two existing theories, was that the quantum field describing the electron necessarily contained within it a second field, the positron field. Every particle, the mathematics implied, has an antiparticle. For every ripple that can move one way through a quantum field, there is a corresponding ripple that moves the other way. Matter and antimatter are not separate things. They are two aspects of the same field, two different kinds of excitation in the same underlying structure. This was a profound insight, but the theory that emerged from it, quantum electrodynamics, the quantum field theory of electrons and light, had a serious problem. When physicists tried to use it to calculate anything beyond the simplest cases, they kept getting the same answer: infinity. An infinite mass, an infinite charge, an infinite probability, none of these mean anything. The theory was beautiful in outline, but apparently broken in practice. The problem persisted through the 1930s and into the 1940s, and then, in a remarkable coincidence of independent genius, 3 physicists in 3 different countries solved it simultaneously, each in their own way. Richard Feynman, working in the United States, developed an entirely new way of thinking about quantum processes, visualizing them as a sum over all possible paths a particle might take, weighted by their probability. His approach led to the famous Feynman diagrams, simple line drawings that represent the different ways a quantum interaction can unfold, each diagram corresponding to a term in a calculation. Julian Schwinger, also American, arrived at the same results through a dense and formally rigorous mathematical framework that was, by all accounts, nearly impossible for most physicists to follow. And Shinichiro Tomonaga, working in Japan during the war years under conditions of considerable hardship, had developed an equivalent approach independently and earlier than either of the others. All 3 shared the Nobel Prize in Physics in 1965. And what they had each discovered was a procedure called renormalization, a way to handle the infinities that appeared in the calculations. The basic idea of renormalization is this: the infinities arise because the theory, taken literally, asks you to sum up contributions from processes happening at all possible energy scales, including arbitrarily high ones. But at those extreme scales, the theory is almost certainly not the right description of reality. So you acknowledge that the theory has a limited range of validity. You introduce a cutoff at some high energy, and you absorb the resulting large but not infinite quantities into the definitions of the particle's mass and charge. You are, in effect, saying, the mass and charge we measure in experiments are not the bare values that appear in the original equation, but those bare values plus all the corrections from the quantum field around them, and we fold all of that together into a single number that we simply measure rather than calculate. This sounds at first glance like a trick, like hiding the problem rather than solving it. And Feynman himself, for the rest of his life, was deeply uncomfortable with it. He once described renormalization as a dippy process and expressed frustration that it was not more mathematically clean. But the results it produced were extraordinary. The magnetic moment of the electron, a measure of how strongly the electron behaves like a tiny magnet, was calculated using renormalized quantum electrodynamics to a precision of more than 10 decimal places, and it agreed with the measured value to the same precision. This is the most accurate prediction in the history of science. Whatever renormalization is doing, it is doing something right. And so, by the early 1950s, there existed a working quantum field theory, a framework in which particles were ripples in fields, in which every particle had an antiparticle, in which forces were mediated by the exchange of other particles, and in which the calculations, though technically infinite in their raw form, could be made finite and precise through a carefully controlled procedure. The ocean had been mapped, at least in part. The next step was to understand what the ripples were actually made of. To understand how a quantum field produces what we experience as a particle, it helps to first think about something more familiar, a guitar string. A guitar string, when plucked, does not vibrate in just any way. It vibrates in specific patterns, specific modes, determined by its length and tension. The lowest mode is the fundamental frequency, the main note you hear. But the string also vibrates simultaneously in higher modes, twice the fundamental frequency, 3 times, 4 times, and so on. These are called harmonics. The particular mix of harmonics is what gives a guitar its distinctive tone, different from a violin or a piano playing the same note. What makes this relevant is that the harmonics are discrete. The string does not vibrate at 1.5 times the fundamental frequency, or 2 1/3 times. Only whole number multiples are allowed because the ends of the string are fixed and the wave must fit neatly between them. The allowed vibrations are quantized. They come in steps, not as a continuous range. A quantum field is similar in spirit, though vastly more complex in detail. A quantum field fills all of space, and rather than being constrained by the fixed endpoints of a string, it is constrained by the laws of quantum mechanics and special relativity. These constraints determine which modes of vibration the field can support. And just as a guitar string has a set of allowed frequencies, a quantum field has a set of allowed excitation states. The lowest of these states is the ground state, the condition of minimum energy. In classical physics, a ground state would simply be a field with zero value everywhere, completely at rest. But quantum mechanics does not allow this, for reasons we will return to in a later chapter. The ground state of a quantum field is not zero. It is not still. It is the quietest the field is ever permitted to be, and it is still vibrating, still fluctuating, just at the lowest possible level. When energy is added to the field, when the field is excited, it moves into a higher state. The first excited state above the ground state corresponds to the presence of 1 particle. The second excited state corresponds to 2 particles. The third, 3. Each step up the ladder of excitation adds exactly 1 more particle to the field. A particle, in this picture, is not something that exists separately from the field. It is the field at a particular level of excitation. It is one rung up the ladder. This excitation is not spread uniformly across all of space. When a particle is created, when a collision in an accelerator, say, or a radioactive decay injects energy into a field, the excitation is localized. It forms what physicists call a wave packet, a region where the field's oscillations are concentrated, where the field value is temporarily elevated above the background. This wave packet has a definite center, a definite width, and a definite momentum. It moves through space in a specific direction at a specific speed. From the outside, from the perspective of a detector, it looks and behaves exactly like a particle. It arrives at a point. It deposits a definite amount of energy. It can be counted. But it is still, at its core, A wave. The wave packet is made of many different frequency components superimposed on each other, and the way those components are combined determines the particle's properties. The overall frequency of the oscillation is related to the particle's energy and, through Einstein's famous relationship between energy and mass, to its mass. The rate at which the center of the wave packet moves through space determines its momentum. The spatial extent of the wave packet determines the uncertainty in its position. A narrower packet means a more precisely located particle, but also a wider spread of momentum components, which is exactly what Heisenberg's uncertainty principle predicts. Now, all the particles that exist in nature, and there are many of them, fall into two great families, and the distinction between these families is one of the most important in all of physics. The first family is called fermions. These are the matter particles, electrons, quarks, neutrinos, and their various heavier cousins. What defines a fermion is a property called spin. Spin is the intrinsic angular momentum of a particle, a kind of built-in rotation that is a fundamental feature of the field, not something the particle acquires by actually spinning. Fermions have a spin value of 1/2, or 3/2, or some other half-integer value, and this half-integer spin has a remarkable consequence. The consequence is the Pauli exclusion principle, named for the Austrian physicist Wolfgang Pauli, who proposed it in 1925. The principle states that no two identical fermions can ever occupy the same quantum state at the same time. Two electrons cannot be in the same place with the same momentum and the same spin orientation. They are, in a deep mathematical sense, mutually exclusive. The principle is not a rule that fermions choose to obey. It is a consequence of the mathematical structure of their underlying field, of the way the field's excitations combine when two identical ripples are present. The implications of this are vast. Without the Pauli exclusion principle, all the electrons in an atom would collapse into the lowest possible energy state, and all atoms would be identical, and chemistry would not exist. It is the exclusion principle that forces electrons to occupy different energy levels in an atom, building up the shell structure that gives each element its distinct chemical character. The periodic table of elements is, in a very real sense, a consequence of the exclusion principle. And so is the solidity of matter. When you press your hand against a wall, the resistance you feel is largely the exclusion principle at work. Electrons in your hand refusing to share their quantum states with electrons in the wall. The second family is called bosons. These are the force-carrying particles, photons, which carry the electromagnetic force, gluons, which carry the strong nuclear force, the W and Z particles, which carry the weak nuclear force, and the Higgs boson, which we will meet in the next chapter. And crucially, they are not subject to the exclusion principle. Any number of identical bosons can occupy the same quantum state simultaneously. They are not mutually exclusive. They are, if anything, mutually attractive in the statistical sense, preferring to pile into the same state together. This has its own remarkable consequences. A laser beam is the most vivid example. In an ordinary light source, like a candle or an incandescent bulb, photons are emitted in all directions with a range of frequencies, each one in a different quantum state. But in a laser, a large number of photons are forced into exactly the same quantum state, the same frequency, the same direction, the same phase. They march together. Because bosons can all share one state, there is no limit to how many photons can join the collective. The beam is, in a sense, one enormous excitation of the photon field with an enormous number of ripples all moving in perfect unison. The coherence of laser light, its ability to remain focused over long distances, to carry information with extraordinary precision, is a direct consequence of the boson nature of the photon. A particle's charge, meanwhile, is not a property painted onto the ripple from outside. It is a consequence of how the underlying field transforms under certain mathematical operations, specifically under what physicists call a symmetry transformation. a change in the way the field is described that leaves the physics unchanged. The electron field has a particular symmetry, and the charge of the electron is the number that characterizes how the field responds to that symmetry. Different fields respond differently, which is why different particles have different charges. The photon field has a symmetry that gives it zero charge. The quark fields have symmetries that give them fractional charges, 1/3 and 2/3 of the electron's charge, which combine to give protons and neutrons their whole number charges. Mass, as we will see in detail in the next chapter, is the most subtle property of all. For most particles, it arises from the interaction of the particle's field with a field that permeates all of space, always switched on, always present. But even before we reach that story, it is worth pausing on what we have already found. Every property of every particle, its mass, its charge, its spin, its relationship with other particles, is not a feature of a tiny object. It is a feature of a field. The field is the primary reality. The particle is what the field does when it is disturbed, and the disturbance, the ripple, the wave packet moving through the ancient and patient ocean of the field, that is all that a particle ever is. In the early 1960s, the theory of quantum fields was in a state of partial triumph. Quantum electrodynamics, the field theory of electrons and photons, was working with extraordinary precision. But physicists were struggling to extend this success to the other forces of nature, and they had run into a specific and elegant problem that, on the surface, seemed almost too clean to be real. The weak nuclear force is the force responsible for a certain kind of radioactive decay, the process by which a neutron inside an atomic nucleus transforms into a proton, emitting an electron and a very light, nearly massless particle called a neutrino. This force operates only at very short range, much shorter than the diameter of an atomic nucleus, and it is far weaker than the electromagnetic force at everyday energies, which is how it got its name. In quantum field theory, a force's range is directly related to the mass of the particle that carries it. The photon, which carries the electromagnetic force, has zero mass, and as a result, the electromagnetic force has infinite range. It extends across the entire universe, growing weaker with distance, but never reaching zero. A force carried by a massive particle, on the other hand, has a limited range. The heavier the carrier particle, the shorter the range. This relationship between mass and range is a deep consequence of the mathematics of quantum fields. So when physicists tried to build a quantum field theory of the weak nuclear force, they could see from the force's very short range that its carrier particles, which we now call the W and Z bosons, had to be extremely massive. Measurements would eventually show that the W boson is about 80 times the mass of a proton, and the Z boson is about 90 times. These are very heavy particles by the standards of particle physics. But here was the problem. The mathematical framework that physicists were using to build quantum field theories, a framework based on elegant symmetry principles, required the carrier particles to be massless. The same symmetry that made the theory mathematically consistent and free of infinities also forbade the carrier particles from having mass. If you simply wrote a mass for the W and Z particles into the equations by hand, the theory broke down. The calculations produced nonsensical results. The theory was inconsistent. This was the problem that a group of physicists, working largely independently in the early 1960s, set out to solve. Peter Higgs in Edinburgh, Robert Brute and François Englert in Brussels, and Gerald Guralnick, Carl Hagen and Tom Kibble in London all published related papers in 1964. The mechanism they proposed is now called the Higgs mechanism, and it is one of the most beautiful solutions in the history of physics. The solution begins with an observation about symmetry breaking. Consider a perfectly symmetrical landscape, a smooth, circular valley with a hill in the center, like the inside of a Mexican hat. If you place a ball at the very top of the central hill, the system has perfect symmetry. Every direction looks the same from that point. But the top of the hill is unstable. The ball will roll down. When it does, it will settle somewhere in the circular valley at the bottom, and in doing so, it will break the symmetry. The Higgs mechanism works in an analogous way. The Higgs field, unlike all the other quantum fields, has a potential energy landscape shaped like that Mexican hat. The top of the hill, the field value of 0, is an unstable configuration. The stable configuration, the true ground state of the field, is not 0, but some non-zero value corresponding to a point in the valley. And crucially, the universe settled into this stable state very early in its history, in the hot first moments after the Big Bang, as it cooled. The Higgs field did not gradually build up to its current value. It snapped into it, the way a supercooled liquid snaps into a crystal when it freezes. The result is that the Higgs field, today, everywhere in the universe, has a non-zero value. It is switched on. Unlike every other quantum field whose ground state is 0, whose baseline is silence, the Higgs field's baseline is a constant, pervasive, non-zero presence. It fills all of space with a value that never switches off, that passes through every atom of every planet, through the walls of buildings, through you as you lie here, without diminishing, without varying, a steady background hum that has been present for nearly 14 billion years. And particles moving through this ever-present field acquire mass. The mechanism is not entirely unlike friction, though it is important not to push that analogy too far. A particle that interacts strongly with the Higgs field finds its motion through space resisted, not slowed in the way that friction slows a sliding block, but changed in its character. The particle behaves as though it has inertia, as though it requires energy to accelerate. That inertia is what we call mass. Different particles interact with the Higgs field to different degrees. The top quark, the heaviest of the 6 types of quark, couples to the Higgs field very strongly and is correspondingly very massive. About 173 times the mass of a proton. The electron couples much more weakly and is correspondingly light, about 1800 times lighter than a proton. The photon does not couple to the Higgs field at all, and it has 0 mass, which is why light travels at the speed of light. The neutrino couples very weakly, so weakly that for decades physicists thought it was massless, and we still do not know its mass precisely. The Higgs boson, the particle that the discovery at CERN in 2012 confirmed, is the ripple in the Higgs field itself. It is what you get when you add energy to the Higgs field and disturb it, the same way a photon is what you get when you disturb the electromagnetic field. The boson is not the field, it is the evidence of the field's existence, one detectable wave on an ocean that is otherwise too calm and uniform to see directly. To produce that ripple, physicists built the Large Hadron Collider beneath the French-Swiss border near Geneva. It is a ring 17 miles in circumference, buried about 300 feet underground, lined with superconducting magnets. Magnets cooled to temperatures colder than outer space, colder than the average temperature of the universe itself, that generate magnetic fields strong enough to bend the path of protons moving at close to the speed of light. Protons are accelerated around the ring in opposite directions and made to collide at 4 points around the ring, where enormous detectors, some of them weighing thousands of tons, surround the collision points and record what emerges. In those collisions, which happen hundreds of millions of times per second, the energy of the protons is briefly concentrated into a volume far smaller than an atomic nucleus. For a moment, the conditions resemble those of the universe, a tiny fraction of a second after the Big Bang. In a small fraction of those collisions, enough energy is deposited into the Higgs field to produce a single excitation, one Higgs boson, which exists for an extraordinarily brief time, roughly 100 billion times shorter than a billionth of a second, before decaying into other particles. Those decay products are what the detectors actually see. On the 4th of July 2012, the two main experiments at the Large Hadron Collider, called ATLAS and CMS, announced simultaneously that they had observed a new particle consistent with the Higgs boson. The mass of the particle was approximately 125 times the mass of a proton. Peter Higgs, who was in the audience, was seen to wipe his eyes. He had proposed the existence of this field 48 years earlier, and he had lived to see it confirmed. He received the Nobel Prize the following year, along with François Englert. What had been discovered was not just a particle. It was the confirmation that the universe contains a field with a non-zero ground state, a field that is always on, that permeates everything. That is the reason you have weight, the reason atoms hold together, the reason the world has the structure it has. Without the Higgs field, the W and Z bosons would be massless, the weak nuclear force would have infinite range, and the universe as we know it, with its atoms, its stars, its chemistry, its life. The Higgs field is the ground on which everything else stands, and it was there, quietly and patiently, long before we knew to look for it. Take a container. Make it as empty as you possibly can. Remove every molecule of air, every atom of gas, every stray particle. Cool it to the lowest temperature achievable, close to what physicists call absolute zero, the point at which thermal motion essentially ceases. Seal it from all external radiation. Make it, to the best of your ability, a perfect vacuum, a region of space containing nothing at all. And then ask, what is left? The answer, which quantum field theory gives with quiet confidence, is that what is left is not nothing. What is left is the quantum vacuum, the ground state of all the quantum fields simultaneously, and it is one of the most active, restless, inexhaustible things in the universe. To understand why, we need to think about a principle that Werner Heisenberg articulated in 1927. It is usually called the uncertainty principle, and it is often described as a limitation on measurement. You cannot simultaneously know a particle's position and momentum with perfect precision, because the act of measuring one disturbs the other. This is true, but it is not the deepest truth. The uncertainty principle is not really about measurement at all. It is about the nature of physical quantities themselves. What the uncertainty principle actually says is this: certain pairs of physical quantities are related in such a way that they cannot both have definite values at the same time, regardless of whether anyone is measuring them. Position and momentum are one such pair. But so are the value of a field at a given point, and the rate at which that value is changing, what physicists call the field value, and its conjugate momentum. These two quantities are linked by the same uncertainty relation. What this means for the quantum vacuum is profound. If a quantum field had a definite value everywhere, say exactly zero everywhere, as you might expect for an empty field, then its rate of change would be completely undefined, wildly uncertain, which would mean the field was fluctuating uncontrollably. Conversely, if the rate of change were exactly zero, the field perfectly still, then its value would be completely uncertain. You cannot have both. The uncertainty principle forbids a quantum field from being simultaneously at a definite value and perfectly still. The ground state of a quantum field, the vacuum state, is the compromise between these two extremes. It is the state of minimum energy, but that minimum energy is not zero. It is a finite value called the zero-point energy, the energy that cannot be removed, the irreducible residue of the uncertainty principle. And the field, even in its ground state, is constantly fluctuating around its average value. The fluctuations are random. They average to zero over time, but at any given instant, the field is not zero. It is doing something. These fluctuations have a remarkable consequence. They briefly and spontaneously produce pairs of particles, a particle and its corresponding antiparticle, which pop into existence together, exist for an extraordinarily short time, and then annihilate each other, returning their energy to the vacuum. These are called virtual particle antiparticle particle pairs and the word virtual antiparticle pairs, and the word virtual is important. These are not particles in the full sense. They cannot be detected directly, cannot be stopped and examined, cannot be made to leave a track in a detector. They exist in the space between measurements, in the gaps that the uncertainty principle carves out of our knowledge of the field. They are real in the sense that they have measurable effects, but they are not real in the sense of being observable particles. The energy borrowed to create them is returned almost immediately. How quickly? The more massive the virtual pair, the shorter the time they can exist before the debt must be repaid. This is another expression of the uncertainty principle, the uncertainty in a system's energy, and the uncertainty in the duration over which that energy is measured are linked in the same way as position and momentum. A large energy fluctuation must be brief. A small one can persist longer. The vacuum is constantly cycling through these brief, self-cancelling excitations at all scales of energy and time, simultaneously, everywhere. This is not a theory. It has been measured. The first measurement is called the Casimir effect, predicted by the Dutch physicist Hendrik Casimir in 1948 and first measured experimentally in 1997 with sufficient precision to confirm the prediction. Take two flat, uncharged metal plates and place them extremely close together in a vacuum, separated by a gap of only a few hundred nanometers, a nanometer being a millionth of a millimeter. The plates are uncharged, so there should be no electromagnetic force between them, and yet they are measurably pushed together. The reason is the vacuum fluctuations. In the space between the plates, only certain wavelengths of virtual photon can fit. The gap acts like a resonant cavity, and only oscillations that fit neatly within the gap are permitted. Outside the plates, all wavelengths are permitted. This means there are more virtual photon modes outside the plates than between them, and therefore more vacuum pressure outside than inside. The plates are pushed together by the pressure of the vacuum itself. The force is tiny. For plates a micron apart, it is roughly equivalent to the weight of a few water droplets spread across a square centimeter, but it has been measured and it matches the theoretical prediction with impressive precision. The second measurement is called the Lamb shift, observed by the American physicist Willis Lamb in 1947 and explained theoretically by Hans Bethe shortly after. In the hydrogen atom, the electron occupies specific energy levels, and in the simplest quantum mechanical model, one that ignores quantum field effects, two particular states of the electron, called the 2s and 2p states, should have exactly the same energy. Lamb measured the energy levels with extraordinary precision using microwave techniques and found that they were not the same. The 2s state was slightly higher in energy than the 2p state by a tiny but perfectly definite amount. The explanation is that the electron, even when it is simply sitting in its orbital around the proton, is being constantly and gently jostled by the vacuum fluctuations of the electromagnetic field around it. The virtual photons of the vacuum are always present, always briefly exciting and de-exciting, and their effect is to slightly shift the electron's energy levels. The 2s and 2p states respond differently to this jostling. Their charge distributions are different, and so the vacuum pushes them differently, and the result is a tiny but measurable energy difference. The Lamb shift was one of the key pieces of evidence that convinced physicists that quantum electrodynamics was the correct theory of electrons and light, because the theory predicted the shift with extraordinary accuracy. So the vacuum, the state of a quantum field when no particles are present, is not empty. It is alive with fluctuation, with virtual pairs briefly appearing and vanishing, with a pressure that pushes uncharged plates together, with a jostling that shifts the energy levels of atoms. The ground state of reality is not silence. It is the quietest possible noise. And there is one more aspect of the quantum vacuum that we should hold gently before moving on. All of these fluctuations contribute energy. The vacuum has energy. And when physicists try to calculate how much energy the vacuum contains, summing up the zero-point energies of all the quantum fields at all the frequencies they can support, they get a very large number. A number that, as we will see in the final chapter of this journey, is in spectacular disagreement with what we actually observe about the universe. The vacuum's energy is one of the deepest unsolved problems in all of physics. But for now, it is enough to know that the nothing is not nothing, that even the most empty space you can imagine is, at its heart, quietly and ceaselessly alive. When you hold a magnet close to a piece of iron and feel the pull between them, something is happening across the space between them. But what, exactly? In the classical picture, we say there is a field, a magnetic field, that extends through space from the magnet, and the iron responds to that field. The field is real, but it is a smooth, continuous thing, a mathematical description of how the force varies from point to point. It does not, in the classical picture, have any internal structure. It just exists. Quantum field theory tells a different and more detailed story. The force between objects is not transmitted by a smooth field. It is transmitted by particles, by discrete ripples in the field that carry the force from one object to another. And the nature of those ripples determines the nature of the force. The electromagnetic force, the force responsible for light, for the behavior of charged particles, for chemistry, for the structure of atoms, for virtually everything you interact with in daily life, is carried by the photon. When two electrons approach each other and repel, what is actually happening is this. Each electron is a ripple in the electron field. Each is surrounded by a photon field that it disturbs through its charge. As the electrons draw close, those disturbances in the photon field, virtual photons, in the language of the theory, carry information about each electron's charge and position to the other. The push is the repulsion. The word virtual here is doing important work. A real photon, the kind that travels from a light source to your eye, is a genuine excitation of the electromagnetic field, a ripple that can travel arbitrarily far, that can be detected, that carries energy. It is a disturbance in the field that exists only within the interaction, that cannot be directly observed, and that is permitted to violate certain rules. Most notably, it can have an energy and momentum that a real photon of the same frequency could not have. It is, in a sense, an off-shell excitation, a ripple that does not satisfy the usual relationship between energy and momentum that real particles must obey. This is permitted because the uncertainty principle allows short-lived fluctuations to borrow energy, and the virtual photon's existence is brief enough that the debt is repaid before it can be detected. The range of a force, how far it reaches, is determined by the mass of its carrier particle. The photon has zero mass, and so the electromagnetic force has infinite range. It weakens with distance, following an inverse square law. Double the distance, and the force falls to a quarter. This is why you can feel the gravitational pull of the sun from 100 million miles away, and why you can receive radio signals from spacecraft at the edge of the solar system. The weak nuclear force is carried by the W and Z bosons, which, as we saw in the previous chapter, are very massive. As a result, the weak force has a very short range, roughly 1/100th of the diameter of a proton. It is entirely confined within the nucleus of the atom. At distances larger than this, the W and Z bosons cannot exist as virtual particles for long enough to carry any influence. The force simply does not reach. The strong nuclear force, the force that holds quarks together inside protons and neutrons, and that holds protons and neutrons together inside atomic nuclei, is carried by particles called gluons. The gluon field is one of the most extraordinary in all of physics, and the force it mediates has a property that has no parallel in everyday experience. Quarks, the fundamental constituents of protons and neutrons, are never found alone in nature. They always come in groups, either in pairs or in triplets. No experiment has ever detected a free, isolated quark. This is called confinement, and it is a direct consequence of how the gluon field behaves. In electromagnetism, the field lines between two charged particles spread out as the particles move apart. The force weakens with distance because the field is diluted over a larger and larger area. The gluon field does not do this. Instead, the gluon field lines are attracted to each other. They bunch together rather than spreading out, forming what physicists describe as a flux tube, a narrow column of field connecting the two quarks. The energy stored in this tube is proportional to its length. As you pull the quarks apart, the tube stretches and the energy stored in it increases. The force between the quarks does not weaken with distance, it stays roughly constant or even grows. This has a remarkable consequence. If you try to pull a quark out of a proton, you are stretching the flux tube. Eventually, the energy stored in the tube is sufficient to create a new quark-antiquark pair from the vacuum. And it does, spontaneously. The tube snaps, and instead of liberating a lone quark, you have produced a new meson. You cannot get a free quark out because the energy required to separate it is always redirected into creating new particles. Quarks are, in this deep sense, permanently imprisoned. The gluons themselves carry what physicists call color charge, a property analogous to electric charge, but with 3 varieties rather than 1, conventionally labeled red, green, and blue. Because gluons carry color charge, they interact with each other as well as with quarks. This is fundamentally different from photons, which carry no electric charge and therefore do not interact directly with each other. The self-interaction of gluons is what causes the flux tube to form, what causes confinement, what makes the strong force so unlike any other force we know. Gravity stands apart from all of this. It is the force you feel most directly, the pull that keeps you on the surface of the Earth, that holds the moon in its orbit, that governs the motion of galaxies. And yet it is the one force that quantum field theory cannot fully describe. Einstein's general theory of relativity describes gravity not as a force in the usual sense, but as a curvature of space-time itself. Mass and energy curve the fabric of space-time, and other objects follow the curves. It is an extraordinarily successful theory, but it is a classical theory. It does not incorporate the principles of quantum mechanics. Physicists believe there should be a quantum field theory of gravity with a carrier particle called the graviton that mediates the gravitational force the way photons mediate electromagnetism. The graviton, if it exists, would be massless, consistent with gravity's infinite range, and it would have a spin of 2. But every attempt to build a consistent quantum field theory of gravity along the lines of the other forces has failed. The calculations produce infinities that cannot be removed by renormalization. The theory is not renormalizable, which means it breaks down at short distances and high energies in a way that cannot be patched. This is not a small technical problem. Gravity is the force that shapes the large-scale structure of the universe. The fact that it sits outside the framework that describes everything else is one of the deepest puzzles in all of physics. And it points towards something that the fields in their current form do not yet tell us, a gap in the map that we will return to at the end of this journey. For now, though, there is something quietly wonderful in the picture that has emerged. Every force you have ever felt, every chemical bond that holds every molecule in your body together, every photon of light that has ever entered your eye, every push and pull between every charged particle in every atom of every object you have ever touched, all of it is the exchange of ripples between fields. Forces are conversations between fields, conducted in the language of particles, happening billions of times per second in the space between your atoms, in the space between the atoms of the floor beneath you, in the space between everything, all the time, without pause. There is a tendency to think of quantum field theory as something remote, a framework that matters only in particle accelerators and cosmological calculations, relevant to the very small or the very energetic, disconnected from the world of ordinary experience. This tendency is understandable, but it is mistaken. The mathematics of quantum fields turns out to be one of the most versatile tools in all of science, and it has illuminated some of the most striking phenomena in the physics of everyday materials. The connection begins with a simple observation. A quantum field is, at its core, a mathematical object that assigns a value to every point in space and time, and that obeys certain rules about how those values can change. Those rules, the quantum mechanical rules of quantization, of discrete excitations, of particles that are either bosons or fermions, are not unique to the fields of particle physics. They apply wherever you have a large number of quantum objects interacting with each other. And in a solid or a liquid, you have exactly that. A vast number of atoms and electrons interacting with each other through electromagnetic forces, collectively producing behavior that no single atom could produce on its own. The study of these collective behaviors is called condensed matter physics, and since the 1960s it has increasingly borrowed the language and the mathematics of quantum field theory to understand what it sees. One of the most striking phenomena in condensed matter physics is superconductivity. In most metals, electrical resistance arises because electrons moving through the material are scattered by the vibrations of the atoms. They bump into the lattice, lose energy, and that lost energy appears as heat. Resistance is, in a sense, friction for electrons. But in certain materials, cooled below a critical temperature, the resistance vanishes entirely. Not approximately. Exactly. A current set flowing in a superconducting ring will continue to flow for years, for decades, without any driving voltage, losing no energy at all. The explanation, worked out by John Bardeen, Leon Cooper, and John Schrieffer in 1957, is one of the great triumphs of quantum physics. In a superconductor, electrons do something that electrons are not supposed to do. They pair up. Normally, two electrons repel each other because they are both negatively charged. But in a metal, the electrons are not moving through empty space. They are moving through a lattice of positively charged ions, and that lattice can vibrate. As an electron moves through the lattice, it attracts the nearby ions slightly, creating a small region of increased positive charge density in its wake. A second electron, arriving shortly after, is attracted to this region. The net effect is a weak attraction between the two electrons, mediated by the vibrations of the lattice. The pairs that form are called Cooper pairs. Here is where quantum field theory enters. Cooper pairs are made of two electrons, and electrons are fermions. But two fermions combined can behave as a boson, because their half-integer spins add up to an integer. And bosons, as we discussed, can all occupy the same quantum state simultaneously. Below the critical temperature, all the Cooper pairs in a superconductor condense into a single collective quantum state. They all share the same quantum description, moving together in perfect unison, a macroscopic quantum object of enormous extent. This collective condensation is described mathematically using the same language as the Higgs mechanism. A field acquiring a non-zero ground state value, breaking a symmetry, producing a new kind of order. The mathematics of superconductivity and the mathematics of the Higgs field are, at a deep level, the same mathematics in different clothes. Because all the pairs are in the same state, they cannot be individually scattered by the lattice vibrations that cause ordinary resistance. The collective state is rigid. It resists perturbation. An electron cannot be knocked out of step with the others because there is nowhere else for it to go. The result is zero resistance. A similar story can be told about quantum phase transitions, the point at which a material changes from one collective behavior to another, not because of temperature, but because of some other parameter, such as pressure or magnetic field. Near these transition points, the collective behavior of the electrons in the material can be described by a quantum field that is on the verge of acquiring a new ground state. The fluctuations of this field, the quantum analog of the thermal fluctuations near an ordinary phase transition, control the material's properties in ways that can be calculated using quantum field theory techniques. The field theory of the transition point turns out to be mathematically identical, in many cases, to the field theories of particle physics. And then there are quasi-particles. In a material containing billions of electrons all interacting with each other and with the lattice of atoms, the individual electrons are not the right objects to think about. What matters is the collective excitations of the whole system, the ways the system can be disturbed from its ground state. These collective excitations behave, in every experimentally measurable way, like particles. They have definite masses, definite charges, definite spins. But they are not fundamental particles. They are ripples in the collective field of billions of interacting electrons, the same way a sound wave is a ripple in the collective behavior of billions of air molecules. They are called quasi-particles, and some of them are very strange indeed. There are quasi-particles with a fractional electric charge, a third of the electron's charge, that emerge in certain two-dimensional electron systems in strong magnetic fields. There are quasi-particles that behave as though they are their own antiparticles. There are quasi-particles with exotic properties that do not correspond to any known fundamental particle. The existence of quasi-particles is a profound lesson in what it means to be a particle. A quasi-particle is indistinguishable from a fundamental particle by any measurement you can make on it in the material. Its mass, its charge, its spin, its interactions, all are as definite and reproducible as those of an electron. The only way you know it is not fundamental is by stepping outside the material and remembering that it is made of something else. But inside the material, from the perspective of the physics happening there, the quasi-particle is as real as anything. This raises a question that physicists do not entirely dismiss. How do we know that what we call fundamental particles are not themselves quasi-particles, collective excitations of some deeper structure that we have not yet discovered? The electron may be fundamental in the sense that we have not found anything beneath it, but that is not the same as knowing there is nothing beneath it. The frontier of this work now involves quantum computers. Simulating a quantum field, even a relatively simple one, even with a modest number of particles, requires tracking an exponentially growing number of quantum states. A system of 100 particles has more possible quantum states than there are atoms in the observable universe. Classical computers cannot handle this. But a quantum computer, a device that itself operates according to quantum mechanical principles, using quantum bits that can be in superpositions of 0 and 1, can, in principle, simulate quantum systems efficiently, because it is itself a quantum system. Researchers are now building quantum algorithms to simulate lattice gauge theories, quantum field theories defined on a grid of points, which is how the strong nuclear force is often calculated in practice. The goal is to simulate the behavior of quarks and gluons in conditions that are impossible to achieve in accelerators, the interior of neutron stars, the first microseconds after the Big Bang, the transition between ordinary matter and a phase of matter called quark-gluon plasma, in which quarks and gluons are no longer confined inside protons and neutrons but move freely. These simulations could reveal new physics, new phenomena, new understanding of the fields that underlie everything. And the same quantum computers that might one day simulate the early universe are being built, in part, using superconductors, materials whose behavior is explained by the same quantum field theory that describes the early universe. The circle closes quietly, the way a good night's thoughts tend to do, each idea connecting back to the one before it. Every map has an edge. The most honest maps mark that edge clearly, not with a warning, not with a declaration of failure, but simply with the acknowledgement that beyond this line we have not yet been. The map of quantum field theory is extraordinary in its reach and its precision. It covers more of the territory of physical reality than any other framework humans have ever built, and it has an edge. we have already glimpsed one aspect of that edge: gravity. The force that governs the large-scale structure of the universe, that shapes the paths of planets and the fates of stars, sits outside the quantum field framework in a way that the other three forces do not. But there is a second, deeper problem that sits at the heart of the relationship between quantum fields and the universe as a whole. It is called the cosmological constant problem, and it is, by any reasonable measure, the largest quantitative disagreement in the history of science. The cosmological constant is a number that describes the energy density of empty space, the amount of energy per cubic meter contained in the vacuum itself. It was first introduced by Einstein in 1917, removed when he thought it unnecessary, and then reinstated by cosmologists in the 1990s when observations of distant supernovae showed that the expansion of the universe is not slowing down, as gravity would cause it to do, but is accelerating. That something is the energy of the vacuum, the dark energy, and the cosmological constant is the measure of how much. The measured value of the cosmological constant is extremely small. It corresponds to an energy density roughly equivalent to a few hydrogen atoms worth of energy per cubic meter of space, a tiny, tiny amount. The universe is expanding, but very gently, very slowly, and the energy driving that expansion is extraordinarily dilute. Now, quantum field theory also predicts a value for the energy density of the vacuum. The vacuum is full of fluctuations, as we have seen, and each mode of each field at each frequency contributes a zero-point energy. Add them all up, and you get the vacuum energy density. The problem is that when you perform this calculation, summing up contributions from all the fields we know about, up to the highest energies where we trust the theory, you get a number that is roughly 10 to the power of 120 times larger than the observed value. 10 to the power of 120. To put this in some kind of perspective, the number of atoms in the observable universe is approximately 10 to the power of 80. The number of atoms in the observable universe squared is 10 to the power of 160. The disagreement between the quantum field theory prediction of the vacuum energy and the observed cosmological constant is larger than the square of the number of atoms in the observable universe. It is not a rounding error. It is not a subtle miscalculation. It is a discrepancy so vast that it suggests something fundamental is missing from our understanding. Various solutions have been proposed. Perhaps there is a cancellation mechanism, some unknown principle that causes the contributions from different fields to nearly perfectly cancel each other, leaving only the tiny residue we observe. Perhaps the cosmological constant is not truly constant, but varies slowly over cosmic time. Perhaps our understanding of the vacuum energy is simply wrong, and the calculation is not as straightforward as it seems. No proposal has gained universal acceptance. The cosmological constant problem remains open, a gap in the map so wide that you could lose entire theories in it. The second edge of the map is found at a scale so small it is almost impossible to imagine. It is called the Planck length, and it is approximately 10 to the power of minus 35 meters. To give you a sense of that scale, a proton is about 10 to the power of minus 15 meters across. The Planck length is 10 to the power of 20 smaller than a proton. It is to a proton what a proton is to something roughly the size of the solar system. At the Planck length, something happens to space and time themselves, our current understanding of both. Quantum field theory's picture of fields living on a smooth, continuous space-time background, and general relativity's picture of space-time as a curved but smooth geometry, is expected to break down. At this scale, the quantum fluctuations of space-time itself become significant. Space is no longer a smooth backdrop for fields to live on. It is itself fluctuating, uncertain, possibly granular. The concepts of distance and duration that underpin all of physics become ambiguous. Two major theoretical frameworks attempt to describe what lies at and below this scale. The first is string theory, which proposes that the fundamental objects of nature are not zero-dimensional points, as particles are in quantum field theory, but one-dimensional vibrating strings whose different vibrational modes correspond to different particles. In string theory, gravity arises naturally as one of the modes of the string, and it is automatically consistent with quantum mechanics. The theory also predicts extra dimensions of space beyond the three we experience, curled up at scales too small to detect. String theory has produced beautiful mathematics and unexpected connections between different areas of physics, but it has not yet made predictions that can be tested by current experiments. The second framework is loop quantum gravity, which takes a different approach. Rather than replacing the point-particle picture with strings, it attempts to quantize space-time itself to apply quantum mechanics directly to the geometry of space and time. In loop quantum gravity, space is not continuous but is made of discrete, indivisible units of area and volume at the Planck scale. Space-time has a granular structure, like a fabric woven from loops of field. This approach preserves the insights of general relativity while incorporating quantum principles, but it too lacks confirmed experimental predictions. These two frameworks are not the only candidates. There are others, including causal set theory and various approaches based on the holographic principle, the idea that the information content of a region of space is encoded on its boundary rather than its interior. All of them are attempts to describe the same thing, the physics beyond the edge of the map, at the scale where our current understanding dissolves. And yet, for all that we do not know, what we do know is extraordinary. We know that the universe is filled, from edge to edge, with quantum fields that have been present since the first moments of time. We know that every particle that has ever existed, every electron, every photon, every quark, is a ripple in one of those fields, a localized excitation of a medium that stretches unbroken through all of space. We know that forces are conversations between fields, conducted through the exchange of particles. We know that the vacuum is not empty, but alive with fluctuation. We know that the mass of everything that has mass arises from the interaction of fields with the Higgs field, which is switched on everywhere, always, a quiet and pervasive presence underlying all of matter. And we know something quieter than all of that, something that requires no mathematics and no experiment to appreciate. Every atom in the body lying here in the dark is itself a pattern of ripples. The electrons in those atoms are not tiny balls orbiting a nucleus. They are excitations in the electron field, standing waves in a field that passes through the walls of this room and out into the street, and up through the atmosphere and on into the dark between the stars. The quarks inside the protons, inside the nuclei of those atoms, are bound by gluon fields whose flux tubes connect them with a force that grows as they are pulled apart, holding them together with a patience that has not faltered since the first seconds of the universe. The light that entered your eyes today was a ripple in the electromagnetic field, a photon that began its existence as an excitation and ended it by being absorbed, its energy transferred, its ripple smoothed back into the field. You are not made of things. You are made of patterns in fields that have no edges, that stretch through everything, that connect you to the floor and the earth below it, and the space above, and the ancient light of distant stars. And right now, in this moment, they are passing through you as quietly and as completely as they pass through everything else in the universe. The questions at the edge of the map. What happens at the Planck scale? Why the vacuum energy is so small, how gravity fits into the picture, are not failures of understanding. They are the universe's way of remaining a little larger than our knowledge of it. Every map that has ever been drawn has had an edge, and every edge has eventually been explored. The people who will draw the next map have not yet been born, or are children now, or are lying somewhere in the dark tonight, half asleep, letting ideas drift through them the way fields drift through everything. The fields are patient. They have been waiting 14 billion years. They can wait a little longer. And so we leave it here, at the edge of what is known, where the map runs out and the dark begins. Somewhere behind you, the day has already grown distant and quiet. The fields that fill this room are undisturbed. The ripples in the electron field that make up your hands, your breath, your slowly closing eyes, they are settling now, finding their ground state, their quietest possible condition. Drift now, if you are ready. Sleep well.